All right, so let's get this started because it's already 8:35. So thank you for waking up really early and showing up at 8:30. We have, as promised, some guests, judges here today. We have Bill and Mark from Google. You may have known some of Bill Mark's software artifacts. One of them is called ISPC. So there's no need to explain ISPC to any of our judges, probably.
That's mostly that part.
That's true, actually. We should give plenty of credit to Matt Farr. But he was already a judge here, so we already gave credit. We also have Ron Babbage from NVIDIA. And Ron, are you in the CUDA group?
I'm in Arch.
You're in Arch now? Okay, sorry, okay. But Ron will definitely be able to know everything that you're talking about CUDA, for sure. And we also have Clem Cole from Intel. And Clem is a CMU alumnus himself. Was it ECE?
ECE, and the guy that's writing Unix in this place.
That's true. So we have some very distinguished judges for you today. I think I'm going to get out of the way, but I just want to say exactly how this is going to unfold. So all of our speakers have exactly 8 minutes. Karima is going to be bad cop. She will cut you off at 8 minutes. We have to move on. Your talk should probably stay around 6. So Karima is going to give you a 5-minute warning when you're 5 minutes into your talk. She'll give you a 7-minute warning when you're 1 minute from being yanked off the stage. And we would love to hear about your projects a lot more than that, but we just also want to get out of here by 11:30. So we're going to have to keep everybody to that. If you are next in line, please come and sit down here so that when the project in front of you is answering questions, we can get you hooked up with AD. So the next group, I don't know, I can't remember the schedule. So whoever's next to you, please come and sit down by the podium. So I'll let you do that. And as promised, we have a number of fun prizes donated by fun companies that probably want to hire you. So we have things like a drone from Hudson River Training. We have Kinect from NVIDIA. We have 2 GoPro Silvers from a friend of ours at Splice Machines. This is going to go on. We have an Apple Watch unopened, but previous generation, I apologize. It's actually a donation from a prior student in 418 that was a thank you for the class. So he donated, he passed it on for We have a Chromebook from Google. We have an Oculus DK2, not a shipping Oculus, but a DK2. What else do we have here? We have a number of cool IoT things from Intel, actually, like an IoT development kit, smart light bulbs, and there's also, courtesy of Uber ATC, 2 $100 Uber gift cards, and our annual Dropbox prize, 10 gigabytes, I think for life, on Dropbox. Courtesy of Carrie, who was our TA last year. So the way this is going to work is that everybody will present. The judges will go deliberate. They have been chosen. They've been told they can choose the winners in whatever metrics they so choose. And when we announce the finalists, first team picks their favorite prizes, and then the next team picks their prizes, and so on, until we run out of prizes, and then we all go home. Okay, so I will turn it over to you guys, and let's get started.
Okay.
It's all yours.
Hello, everyone. Our project is called Gregor, which is a worker pool-based multi-thread programming framework. So the first question is why we want to have Gregor. Because the answer is simple, because parallel programming is really, really hard. The programmer needs to take care of everything, such as task partition, synchronization, communication, and potentially new syntax if you want to use a new language. And also, commercial systems like Silk is not cheap. If you want to use Silk, you must have $700 in your hand. So we want to offer similar semantics and interfaces like Spawn and Sync in Silk, and comparable performances in C, and of course without any cost. To review what is Spawn and Sync, here is an example of Fibonacci sequence written in a Gregor library. The logic of Fib is simple. it will spawn two children to compute sub-problems and then think to return the result. At each spawn site, the programmer specifies that the invoked job can run in parallel with the current one, and when reaching the sync point, the control flow will not resume until all the spawned jobs return. The runtime system will take care of the scheduling policy. Okay, then we'll go into more details.
In principle, it's hard to go beyond the state of art due to the intrinsic limit of our assumption. User's C program have to be compiled as how they are written. In contrast, the Silk is another layer of C. So before the C compiler actually takes over, Silk will do a lot of work to transform your code in order to make the runtime more lightweight. And next, we will, with the Fibonacci example, we will show the path of progressive optimizations we use to approximate the state-of-art performance and give a brief overview of how we structure our runtime library. This is the structure of the first version of Gregor. At the spawn, we will interact with the OS to get a page size stack for the newly created job. And we will set up all the environment in the stack. Then we will enqueue the job into a global job queue. The workers will pull the job out of the queue and context switch to that job. And the job might be re-enqueued before it actually finishes and resumed by another worker. To provide such a flexibility that a job might be executed by different worker threads at different stages, it's a necessary condition to have a per job stack and you cannot avoid this overhead. Note that this allocation of stack and deallocation of stack involve two kernel traps and page searching inside the kernel via the virtual memory subsystems. And to reduce the overhead of kernel trap, and the first optimization is to buffer all the deallocated pages for the later allocation use. So the structure becomes something more like this. And this speed up by a factor of 10. And the next obvious bottleneck is the global shared queue. And we replaced the global queue with the private double-ended queue for each worker and implemented the worker stealing algorithm on top of that. Now at the spawn side, it still gets the stack from the buffer, but instead of enqueuing it into a global queue, the spawning worker will enqueue it into its private queue. And when finish one job, the worker will pull the next job from its private queue to execute. And if the queue is empty now, it will randomly pick up the victim and steal his jobs. And to avoid the risk condition, each DQ access is protected by a separate lock. And this algorithm can bring us a speed up by another factor of 10. And then we focus on reducing the synchronization overhead of DQ access and implement a protocol such that pushing a job into the DQ never needs any locks. And by a very big chance, popping from work's own queue also need no lock at all. And we also find that the calling convention of the GCC can save us a lot of context-saving work. Thus, we can reduce a lot of memory operations. And the combination of these two approaches will reduce the overhead of roughly 30%. And it takes us quite a long time to go any further. But luckily, we find that there's one frequently accessed data structure which is allocated contiguously in the memory at the array, and each worker is guaranteed to access its own copy, which indicates that if the alignment of this data structure is not appropriate, the cache coherence traffic can be non-trivial. So we aligned it with the 128-byte boundary, and this brought us a huge improvement of another factor of 4. And we finally enable the GCC optimization and reach where we are now. And the runtime reduced from the 23 seconds for the fifth with the input 30 to roughly 0.07. And this is where we are now. And next, we show the performance of Gregor compared to Silk and the serial version of the algorithm. on a number of benchmarks. And we take the experiment on late days, which can have at most 24 worker threads. And we see that on most benchmarks, the Gregor is comparable in performance with the state-of-art Silk implementation. And by the way, due to our current implementation, the Gregor have to run in 32-bit mode, while the Silk is compiled in 64-bit mode with more registers, longer word length, and cheaper calling conventions. And the final two graphs will show the scalability of the Gregor compared with Silk on two benchmarks with different number of workers, ranging from only 1 worker to 24. And this basically shows that they follow the same trend, where the Gregor has slightly more overhead, which, as we stated before, is expected. And that's all. Question? And any questions?
So what subset of Silk did you?
Spawn and Sync. Yeah. Okay.
Okay. So the specific problem I was working on is related to a software package that's distributed by the research group that I work for. So in particular, we're interested in doing drug discovery. And a question that we care about a lot is how strongly do two molecules bind? So we'll have a protein of interest, some molecule that typically has biological significance, and we'll want to try to find something that looks like it would work as a drug. So it needs to interact really strongly with this protein that we care about. And often we'll know something about it to begin with. So we'll know that there is a molecule that interacts strongly with it already, and we can do a similarity search in a database to find a database that has like existing drugs or other known small molecules, and use that to return a bunch of things that look like they might bind. But unfortunately, when they're first returned in this method, they have certain interactions that might be really non-physical. And so if we were to calculate something to represent the energy of the interaction in the state that they are returned in, it would end up having a really unrealistic estimate of the energy. Because, for example, so this shows like an example of the program that we have that runs this minimization over several iteration cycles. So you can see that it starts to move more into this pocket, but when it starts out, there's actually a really bad overlap with this surface, which represents like electron cloud, basically. So we actually have like electron clouds overlapping each other, which is really non-physical. And so if we calculated an approximate energy with this starting pose, we would get it would be really high, and we would rank it really poorly when actually it's not a bad binder at all. We also maintain a web server that allows people to do virtual screening, which is what this process is called, in their browser. So people can set up this query and search a database of compounds that we've made available from actually there are several. And then they typically want to minimize the hits that they've returned before they actually get the compounds with this score, which is meant to represent the energy of the interaction, so that they can rank these things and say, okay, the top 10 have really good scores and they look like they might bind really well. But we allow people to minimize 1 million requests at a time. So it would be really nice for us to handle this more efficiently than we currently do with the CPU implementation of this software package. So the way the algorithm works for energy minimizing is we have actually what ends up, the scoring function is just like an algebraic sum of terms that are weighted. And so we can do a pairwise calculation over all the energies in the small molecule that we returned. They're mobile, so they're the things that we're letting move. And the rest of the receptor, this like big surface that you see, is going to stay in place. And we're going to calculate pairwise interactions between the two molecules. And then we also are going to get forces. And you can, anytime you have like a scalar potential energy function, you can write the negative gradient of it as a force. So the gradient, which is what we're going to use to find a minimum, is the forces that these atoms experience. So we compute the energy and the forces, and then we actually represent the small molecule as a tree, where so several of these subunits are rigid, but they're connected by bonds that can rotate. So we want to allow flexibility by allowing them to move. So we pick one rigid center as the root of the tree, tree, and then it is joined by bonds in the physical space to other nodes in the tree that are its children, to which it's connected. And there are subtrees that are rooted at its children that go to the things that they're bonded to. And so we propagate the forces and torques over this tree of torsions to find what the net force and torsions are on this small molecule. So first, we just have a naive CPU implementation, and so it's trivial to parallelize over the number of ligands that we have in the input. So like I said, we might have 1 million ligands. The first logical thing to do is to parallelize over them. So the way I handled this is by having a single reader thread that goes through the file and sets up jobs using the data structures that we have to do all of the scoring function evaluation and minimization. It adds the jobs to a work queue, and then there are some number of NCPUs, threads that are launched that actually do the minimization, and then we want to preserve the ordering of the ligands in the output because we want to compare the starting and ending poses with each other to see how much they moved. So then there's a single writer that pops the outputs off and makes sure that it orders them in the output in the same order that they were in the input. And this ended up being fairly straightforward. It ends up scaling roughly linearly in the number of execution contexts that you have. And so then the next thing is in the scoring function evaluation, which is the part where you're calculating the energies and forces, those are done pairwise. And so each of the calculations over the pairs can be done independently of each other. And then for a given ligand atom, so if this is being done on the GPU, there's a block launched for every ligand atom, and the pairwise calculations of the receptor atoms are performed in parallel, and then there are several reductions that are done over energies and forces. So this ended up being the initial bottleneck in the code, and I ended up seeing that Mark Harris had published a sequence of reductions that he had done, optimization steps with reductions. And so the thing that he found being most optimal was a warp-based reduction that I was able to adapt and use for this code with minor modifications. And just the main point is that previously, without using this reduction approach, there were several shared memory accesses that might be at disparate locations, and there also were several synchronizations that had to be applied. But by doing the reductions across warps, I was able to use a shuffle intrinsic instruction to share register values instead of having to touch shared memory. And then after, it only requires 2 stages of reduction, and the first one just requires 32 elements to be written to a shared memory buffer, and then the 0th warp does another just round of this shuffle down where like if you have 32 elements, first you do a sum across like 16, the one 16 ahead of me, then the one 8 ahead of me, then the one 4 ahead of me, etc., until warp 0 has the final value. So then several other optimizations ended up just producing improved performance on just this scoring function evaluation, calculating energies and forces. In particular, by packing, a lot of times we're passing around float 3s, but there's another datum that can be packed with it. So by that will be accessed around the same time. So by packing all these things into float 4s and using the align keyword, I was able to get coalesced reads and writes, which was really beneficial. Also using asynchronous mem copies ended up being a huge payoff. And so over this series of optimizations, I ended up seeing around a 3x speed up just by parallelizing the scoring function evaluation. This was being done on the GPU. So the biggest payoffs were coming from the warp reduction, which was a huge speed up. And then this is asynchronous mem copy. Am I out of time? One more minute, okay. But then by doing some profiling, I could see that the GPU was actually underutilized. NVProf said that actually register uses were so high that I was only getting 1 block scheduled per SM, and you can kind of see also that the speed up is better as there are more ligand atoms to parallelize over. So like in many use cases, the GPU is underutilized. Additionally, there was a lot of time spent in doing mem copies and mem sets. So this is like kernel evaluation for doing the scoring function, and then mem copies and mem sets. And actually for each minimization cycle, it does the scoring function evaluation on the GPU, then transfers back to the CPU, decides whether it's converged, and then if not, it goes back to the GPU, doing transfers back and forth each time. So this is like the torsion tree representation of the ligand, as I mentioned, and it would be nice if that were on the GPU because we convert to internal coordinates to reduce the number of coordinates we have to consider. But unfortunately, the host code is written in beautiful object-oriented programming style, and I ended up trying to use unified memory to make this work conveniently without having to completely restructure the program, and there was a precipitous drop-off in the performance. So now, yeah, I have to flatten everything and not use unified memory.
Yes, please.
Hi, so my name is Patrick Koenig.
I'm Nate Horn.
And so our project was PIMD. So, I'm going to go to the next slide. So PIMD is essentially a SIMD insurance library for the video core GPU found on all Raspberry Pi models. So you may not know that a Raspberry Pi comes with a GPU. It's integrated into the CPU, and we wanted to take advantage of this computing power. We wanted to do it in a way that provided an easy-to-use interface. So we want to make it really easy for even novice programmers to take advantage of this powerful hardware and sort of use it on general-purpose parallel computations. So we had three major goals.
Sorry.
Yeah, so our three major goals of the library were for it to be accessible, flexible, and powerful by sort of limiting the overhead that it was introduced with our library. So just going into the architecture of this GPU a little bit. So at the core of the GPU is a set of 12 special purpose processors called quad processors. So for all intents and purposes, each QPU is a 16-way SIMD processor. Has two ALUs, an add ALU and a multiply ALU. They each can perform different instructions, and you can actually perform an add and a multiply operation in the same clock cycle, which is kind of cool. And then the execution context for each QPU consists of 4 accumulator registers, 32 general purpose registers, and then 32 registers for a lot of I/O things. And all of those registers are 16 wide. So they're really wide SIMD cores, so you can do a lot of computation at the same time. So now that we have these QPUs, how do we get data to and from the GPU? So there are a couple components on the GPU in order to get memory in and store it out. So the first one is uniforms. So uniforms are basically a way for the GPU to read a sequential block of memory. So usually this is used to read in function arguments. You can think about passing function arguments as just passing them in a contiguous block of memory. And then the GPU can just read them in by reading a register. The second major component is the TMU. This is essentially used for general memory lookups. We can use it to read in sort of large vectors of input data. And then the third major component is the VPM. The VPM is a 4 kilobyte shared memory buffer. The QPUs can populate it, and then you can initiate stores out to main memory from it. So the diagram over there is just an example of sort of the block layout of the VPM. So traditionally, QPU programs need to be written in a QPU-specific assembly language. And actually, when we're at the beginning of our project trying to go through and understand how this worked, it was a little frustrating because it's very not well documented. Broadcom did release documentation for it, but they only did so at the end of last year, and there's sort of a lot of things missing from it. So it was a lot of trial and error. So yeah, as we're going through this, we noticed a couple pain points with implementing code in this way. So the first one is that there are a lot of special rules and restrictions on what registers can be used and how they can be used. So a couple weird examples are when you do branch statements, the branch isn't actually executed until 4 instructions later, and that's where the program counter offset is calculated from. So that makes it a little confusing and frustrating to use. And also for those 32 general purpose registers, you can't read them the instruction following a write. So these are just a couple examples of the really sort of nitpicky things that aren't well documented that you would have to be aware of if you wanted to write QPU assembly programs. And just in general, it requires a lot of register I/O and a lot of knowledge about the GPU architecture in order to get things working correctly. And so after sort of investigating this, we realized that writing QPU assembly code is not very accessible, it's not very easy, and it's really easy to go wrong by not realizing some really minute thing about the way it operates. So in our library, we sort of sought to relieve a lot of these pain points and make it really easy to run code on the GPU, just get it up and running really easily. So in our design, there are sort of 3 major components to our library. The first one are operations. So operations basically just define operations you can perform on the GPU. So for simple instructions, such like adds, bit shifts, and like ands and ors, we basically map those directly to the assembly instructions because it's pretty straightforward what they do, and to give the user sort of a lot of power and control over what they're doing. Then we sort of abstracted away a lot of the more complicated things. So things like loads and stores, which require synchronization and locking, we sort of abstracted those away into sort of single ops to make it really easy for the user to use. And then we define functions as just a series of operations. And we work to transparently handle inputs of any length. So you can define a function with a series of operations and then pass it arguments of any length, and it will loop the function appropriately to handle those inputs. So from the user's perspective, all the elements in your array are being operated on simultaneously, and our library will handle sort of the loading and storing of each section of the inputs. And then you just pass arguments very transparently and easily. Like you pass scalars and vectors in the same way, sort of just like making any function call. You just pass an array of arguments. So we have a short example program here at the side, an example of Saxby.
Yeah, so if we check out this example, up on the top we have all the operations that we're doing. So we're doing a load, a multiply, an add, and then a store. So if you match those up with the arguments, we load x, multiply it by a scale, which is just a float. So that's populated among all of the QPUs in a uniform fashion. So it multiplies x by the scale, then adds y, then stores it off into the result array. And that is all handled by the function.call, which is right there.
Yeah, right. So notice that our thing handles the input sizes. You don't have to, you specify the input size, and it'll deal the code automatically. So just diving into the implementation a little bit, we sort of covered this a little bit. So operations are implemented as short assembly stubs, which we compile when you compile the library. And then when you set up your function, we basically translate these operations into a series of the compiled assembly stubs in order to generate the bytecode that's right on the QPU. And so when we do this, we sort of rearrange the operations in order to prefetch memory. So there's hardly any wait for when you want memory from main memory because we prefetch those. And like I said, we handle arbitrary input sizes. And we also load arguments transparently. So notice in the code, we didn't have to say load this argument and then apply it. It'll handle all the loads of the arguments automatically, including prefetching. And then when you actually call the function, it sets up the shared memory region with all the arguments you passed it. And then when it comes to the actual execution, we divide up the work among 8 of the 12 QPUs. We stuck with 8 just because then it's easy to divide up the 4 kilobyte shared memory buffer into 512 bytes per QPU.
All right, so I'm going to be talking about the results now. So we tested this mainly on 3 things, or we tested this against 2 different other implementations, just the sequential CPU version, the Neon implementation of ARM, or in the ARM libraries that's available on the Raspberry Pi, and then our library. So this was all done on the Raspberry Pi 2, and so we did Saxby, which I talked about a little bit before, just a floating point operation, or just a floating point operations maximization function, which just did 100K, 200K, up to 400K operation just in a row on the same elements, and then bandwidth bound tests of just doing loads and stores. So Saxby, we gained about a 3.41 speed up over Neon, which is pretty good. This is actually the Neon was pretty slow, which was surprising. I think that had to do with the older ARM processor that's located on the Pi 2. I'm running out of time, so I won't have to speed through these. Compute bound, this is to be expected. Our library just crushed the sequential implementation because, it is a GPU. So we had about a 40 times speed up, which is about expected and about as fast as we can get with the operations. And then bandwidth bound test. And bandwidth bound test is actually what mirrors the Saxby implementation of a 3.8 speed up and a 2 times speed up with the Neon, which was good. And all together. And yeah, I guess we ran out of time. Sorry.
It's with the invade, so.
Yeah.
Sorry.
Sorry.
Sorry, you just tested, you didn't build anything with it yet.
I actually built a Gaussian blur, and I'm working on. There's 1 or 2 bugs with that, so I'm still like ironing those out. But after the Gaussian blur, I was going to work on some engineering other compliments stuff.
Okay, so propaganda is a parallel ROP attack
generator. So what a ROP attack is it's a way to hijack control flow of a program. So what you do is, say you have a program with a buffer overflow vulnerability. One of the things you can do is you can write a string to it that clobbers the return address of the current function. Now in old attacks, what people would do is they'd put code directly in that string and execute it. But now the stack is marked as non-executable, so you can't do that anymore. So instead we use what are called gadgets to get the same effect. So we look through the original code of the program, and we find sequences of the byte code that are terminated by the gadget C3, which is return. This is where the name return oriented comes from. And we go from the sequence to sequence. Each one pops the next one off the stack so that we can string them together, and indirectly perform a series of assembly instructions that do what we want our attack to do. Now the thing is, we might not have the exact set of instructions in these gadgets that we actually want to use. So we often have to find equivalent sequences, such as moving through an extra register or maybe using an add of 0 instead of a move to get things where they go. And so our program finds these sequences in parallel.
Yeah, so we created a parallel ROP attack generator. So what we basically did was perform a search, parallel search on, starting from a desired effect. So it's a sequence of gadgets or like targets. And then we also have equivalence rules where we just apply them onto the target until we reach some kind of sequence where the gadgets are already in the memory. So some of our equivalence rules are as follows. So they expand upwards. So like one move from a source to a destination can can transform into a source to a variable, and then the variable to the destination. So our algorithm basically grows a tree. It starts from the target and then just applies either a gadget, which means it's finished, or it applies a rule and then creates more nodes and then solves them. So this is like how one complete algorithm would look. So we have a target right there, and then gadgets to like kind of look through. So over here we apply a series of rules until we finish, basically get the desired effect, and then it prints out the attack string on the screen, and then you can kind of just like convert that into binary and then input it into the buff to overflow to get the attack on the buffer overflow. Yeah, so the reason our algorithm was difficult to implement was we had to prevent infinite looping. Like when do we just applying cycles of rules, synchronizing variables, and serializing gadgets. So we solved these problems, but we're not going to talk about them here. If you want to know more, check our website. So our approach to parallelism was to take the original target, break it up into pieces, and then assign them to threads. And if there were more pieces than there were threads, we would add the remaining pieces into a global work queue, and then as the threads finish, assign them dynamically to better balance the work. So we wanted to do this to minimize synchronization between nodes, basically, or as threads. So so the only time that they had to synchronize was when they rolled back to where we broke it up. And that's where we had to serialize the gadgets. We did implement another version where we had finer grain synchronization, or finer grain work distribution, but we found that the cost of synchronization far outweighed the benefit of fine grain work distribution. So some of our results, sorry, this is kind of hard to see, but we found that because typical targets aren't heavily imbalanced, so they're pretty well balanced, that means that our work distribution is okay. So that means that on larger targets we get, or the speed up is only limited by attack target size, so on larger targets we get better parallelism. On the other hand, for the rare cases where there is workload imbalance, that means that we don't get as much parallelism, or we don't get as much benefit from our parallelism. However, there are some cases where when we parallelize and it fails in the end, we could get superlinear speedup, because if one small node fails and all of the branches before it are large branches, then we basically see a huge improvement in the speed of when
we
it
short
succeeds.
circuit and actually avoid work that we did in the serial case.
Yeah. So those were our results. So now we have a live demo. Okay, let's see. How do you do
You
this?
can get this.
Okay. Oh my God.
Oh, I can't even see it.
You have to look at the thing.
Okay, so what we have here is an actual attack lab target. If I can see it. So, is this visible? Okay, so.
Wait, actually, hold on. Let me press the button. Okay, now do it.
Okay, so we've got an actual attack lab target here, and we're going to generate the attack for it in real time. So what our program takes, so let's run it on 4 threads. It takes some padding. This is what lines us up with that return address in the attack string. We want a return address to go to after the function completes. In attack lab, this is a function that will notify AutoLab that we finished it. We're going to put in a string payload, which is our cookie. This will be placed after the attack, and then 3 A's, and then our actual target. So we put in the target in an assembly-like language. So our target is, all we want to do is we want to do an arithmetic operation, which is going to be the destination register RDI, and we want it to take RSP and add the hex constant 10 to it, which should point us straight to that string payload we had. So we go, and It's pretty fast. Took like 32 milliseconds. And what you'll see is that it actually took that one arithmetic instruction and turned it into about 10 different things. It's moving through all these extra registers in order to get into that target, and then call that function. And it figured out how to do so without ever clobbering the extra registers. You'll notice like REX is used by multiple paths, but they make sure that they move out of it before they move the next thing into it. And so now this will be difficult because I can't see it, but if I can copy this output, do this.
Oh no.
Here, let me just pipe it out. So I'll put it in again because it was fast enough that it doesn't matter. Okay, so it took like 32 milliseconds, and now what we're going to do is we are going to take this and we're going to pipe it to a program that will turn this into actual byte code rather than just ASCII representations of the bytes, and then we're going to pipe this to the target. And what we'll see is valid solution for level 3. So we just solved the hardest stage of Attack Lab. A 213 student would have probably spent hours working on this. It says failed here because Autolab is not currently accepting solutions, but that is evidence that it actually did try to send in the success message to Autolab. But of course, these targets are, they're designed to be hacked. Can we do something that's maybe a little bit more legitimate?
Okay, well, we did hack a tiny server, but since we ran out of time, we can't really show it, but yeah.
It takes like 2
It
seconds.
takes 2 seconds if you want to see it, like maybe after the competition or something. Yeah.
Let's do it afterwards. Just.
Yeah. Okay.
Okay.
Good morning. My name is David Vernay. This is Matt Perrin. And for our project, we implemented the first ever causal Java profiler. So this is based on results discovered by Professors Emery Berger and Professor Charlie Kurtzinger out of UMass Amherst and presented at SOSP 2015 last year. Professors Berger and Kurtzinger actually gave a talk at CMU last semester as well. And Matt and I found their results very compelling and decided to implement their results for Java. So we're going to start by showing you guys an example of when causal profiling will give you more valuable results than a traditional sampling profiler. So here you see we have this loop here. And assume we want to execute this loop as frequently as we possibly can. So for example, in a web server, the server receives a request, wants to run some logic, and you want to return the response as fast as you can. And so in this loop, we have this do parallel section and this do serial section. In the do parallel section here, 32 threads in parallel execute this expensive function. It takes about 50% of the runtime of the loop. And then in the do serial portion, the main thread executes the other 50% of the runtime for the loop. So you should expect that optimizing either the parallel or the serial portion will have roughly equal optimization in the runtime of the program. But as you see here, what a normal sampling profiler will give you is something like this, which indicates that the parallel portion comprises roughly 97.5, the vast majority of the runtime, because it's just counting the CPU time that all these threads are taking. And it shows that do serial is only 2.5% of the runtime. So a naive programmer might see this and say, well, there's no point in optimizing do serial. It only comprises 2.5% of the runtime, even though it actually may be simpler to optimize do serial, and it would give you the same effect. So running JCause on this example program gave us these outputs. On the x-axis here, you have the line speed up percent, so by how much are we optimizing the line. And on the y-axis here, this is the throughput improvement percent, so by how much is throughput being improved by optimizing the line by that much. And as you can see, the parallel portion and the serial portion both indicate roughly a linear speed up to about 35%. And it's not 50% because there's some variance, especially due to Java doing a lot of under-the-hood optimization and stuff like that. But it does correctly tell us that we can expect an equal speed up between the two portions of that loop.
Now we'd like to tell you a little bit more about how causal profiling works and how we've implemented it. So consider a program where you have two threads with a blue portion of code and a green portion of the code, and you'd like to optimize the runtime of that program. What you could do is figure out, if you wanted to figure out what optimizing the blue portion of the code would do, in an ideal world, what you would do is simply speed up the blue portion magically and measure the difference in runtime and run many of these experiments. Since we don't have any magic and we can't just magically speed up the blue portion of the code, what we can do alternatively and get equal results is pause other threads which execute, pause other threads whenever the blue portion executes. And it turns out we get the same difference in speed up, in the difference of execution time. So what we do in our profiler is run many experiments throughout the runtime of a program. So we choose a recently executed line by taking samples. We then choose a speed up for the experiment. And then every time a thread hits that line, every time we see a sample in that line, we pause other threads for a period of time corresponding to that speed up. We then measure the throughput and then collect the results of many of these experiments to generate a causal profile.
So we were able to optimize a well-known Java library using JCause. The library is called the Java H2 Database Engine. It's a widely used mature library. It's been around for a number of years. And we were quite pleased because we were able to run JCause without any prior knowledge of the code base, find an optimization, and implement the optimization within about 1 to 2 hours of using JCause on this library. And so this is the output that JCause gave us for the line that we ended up optimizing. Again, on the x-axis here, you have the percent that we would speed the line up by, and on the y-axis, how much throughput is improved by optimizing the line. And JCause indicates here that we can expect roughly linear increase, again, up to 50% by optimizing this line. And so this is the line that the JCause pointed us to. It's this thread.sleep call here. And what's going on is on a transaction abort, this is just implementing randomized backoff. But what we actually found is that they're sleeping for 1 to 10 milliseconds, which is much longer than they needed to be sleeping to do this randomized backoff. And by lowering that time to 1 to 10 microseconds, it actually ended up giving us quite a nice optimization. So this is the runtime on the left here of H2 before our optimization, and this is the runtime after our optimization. As you can see, it's about 20% faster. And this is also measured using the Decouple benchmarking suite, which is one of the standard suites for measuring Java programs. So again, we were able to do this with no prior knowledge of the code base. JCause pointed us to the exact line of the bottleneck, whereas most other profilers will just tell you the function that's the bottleneck. And we actually ran other profilers on this program as well, and they did not give us this information. Some of them didn't even list the function, others didn't point us to the correct line. So we were quite pleased that JCause was able to do that.
So to wrap things up, we've written the very first causal Java profiler, and we really do feel that this technique provides much more valuable information than standard profilers, like JVisual VM. It allows profiling throughput, not just end-to-end runtime, and it has very little runtime overhead, on par with most sampling profilers. To continue on with this work in the future, we'd like to try to optimize other libraries and see if we can add new features to JCause. One feature we're particularly interested in is latency profiling. And we'd also like to see if there's ways to extend this idea to both multi-process and distributed applications. We are really excited about this project, and we hope you are too. Thank you.
We compared it with HPOF and JVisual VM. And there's another profiler. We use another profiler because Java makes it really difficult to get stack traces asynchronously. So there's another one called Lightweight Java Profiler that we also compared against.
And how well do you think this is going to work on other languages?
Other languages other than Java?
Yeah.
So
the original people who came up with this idea implemented it for a C++ profiler. So that exists already, and our project was to port it to Java.
Stands for Transaction Supervision Extension. And it is an implementation of hardware transactional memory. So it's a tool for dealing with concurrency. So the way this is implemented is using cache coherence. So when a core begins a transaction, it needs to track both the things that it's read and the things that it's modified so that it can determine whether it needs to abort or commit a transaction, right? So the way this works is that it uses the L1 cache to keep track of which cache lines are brought into the cache and which cache lines are modified. So what this means is that when a modified cache line is evicted, then the transaction actually has to be aborted. So this can happen either because of a regular cache eviction or because of a data conflict. On the other hand, though, when an unmodified cache line is evicted, it won't necessarily actually cause an abortion because the processor has a secondary data structure that it uses to track these events, which can then use to check against when someone announces they want to modify a cache line. So other than these cache evictions, there's actually a number of reasons that a transaction can abort. And so when you begin a transaction, there's this instruction called xbegin, and its return code sort of hints to the programmer why the transaction failed. And it only tells you some subset of the things. So some of the things it can tell you is whether there was a data conflict, or whether like the internal implementation buffer was blown, or whether the user specified an abort. But these diagnostics actually don't tell you everything, so you actually need to use profilers to determine what is going on. But these tools are new, and you have to recompile most kernels to get this to work. Other than that, there's a number of things that you would expect to cause abortions, like ring transitions, syscalls, I/O, those sorts of things. And then there's some like less obvious things, like string compare and string copy. These are some subset of the things. And then CPU ID, which is important because debuggers and linkers use these tools.
So yeah, one thing that might not be immediately obvious that you can actually kind of infer from those things is that you really need fallback paths, and one way to do that would be to have a lock. So, for example, you could have two transactions that would just constantly abort each other, and because of that, you would just end up with live lock. So instead, you lock the world, and you do what you would have done inside your transaction. But these transactions aren't actually going to consider the lock because that would defeat the purpose of having transactions. So you need to set a bool to true when you lock it, and to false when you unlock it, and have every transaction read it, so that way they will be aborted if somebody takes the lock. And so using all this, we sort of inferred like a small heuristic that we ended up using, that we need to really be cache conscious when writing our code when involved with TSX. And one of the first rules for that is don't blow your own cache. So we implemented an AVL tree using TSX, and we found that even in one thread, AVL trees have lots and lots of aborts and failures, up to like 60% very quickly. The x-axis here is the millions of inserts, and the y-axis is the failure rate. And it's interesting that even on one thread you get all these failures, and that's because it writes to all these cache lines. And it writes to so many that one of the lines that it writes to actually gets evicted from the cache, so it causes itself to abort. It conflicts with itself.
So another case study that we looked at was treeps. So these are also another form of self-balancing trees, but that don't use rotations. So the gamble here is that treeps don't guarantee to balance the tree nearly as nicely as AVL trees, and in practice we actually saw that the treeps were about twice as deep as AVL trees. So you might potentially touch more data, but we saw that, in fact, this worked rather nicely. And on low thread counts, we saw a very low number of failures. And even on 4 threads, when there was 20% failure rate, we still see a speed up, right? So you see that it still scales with 1, 2, and 4 threads. So something interesting here, though, is that on 8 threads, you see a huge performance degradation. So the machine that we ran this on was a 4-core machine with hyperthreading. And so when you have 8 threads, you have multiple threads on the same core. And so they're both using the same L1 cache, and evictions are more likely. And we saw that this caused a huge number of abortions. Another subtle thing that you need to be aware of is what parts of your data are shared on the same cache line. So when we were implementing a treep, initially, we had to keep some information, like the root node, and then some seed to generate random priorities, right? And since our structs were very small, these things were all kept on the same cache line. And while the root was being read by every transaction, the seed wasn't being read by any transactions. But every thread was modifying the seed, causing a number of transactions to abort. So we saw that just with this naive implementation, 75% of the transactions aborted, but by fixing this, we get the original graph, which is at worst 20%.
So using all this knowledge, we tried to go back to assignment 3 and speed up our paragraph implementation. And in particular, we tried to do BFS, and we actually made it slower. We went from 7 seconds to 10 seconds. And one of the reasons for that is that the critical regions in BFS is really small. It's just a small atomic write. And so there's a fixed cost, we think, to calling xbegin, xend, and just writing to the data, right? So we tried to investigate that, and we said, here's a big array. We're going to increment every element in this array. We're going to do it in batches. So for every xbegin, we increment, say, k elements. And here's a graph showing k from 1 to 16. And at about 6, we think, it crosses over where it starts being valuable to use TSX instead of lockless. And anything before that, you might as well just use atomic operations.
So the takeaways are that debugging TSX can be mysterious. You need to have good tools to diagnose why abortions are actually happening. There's more reasons than just data conflicts. While transactional memory is certainly a great tool and makes writing concurrent code nicer, it's sometimes you still have to think about race conditions. You still have to think about cache lines when you're optimizing. It doesn't solve all your problems. The next is that cache is everything that matters. Well, maybe not everything, but it's a very important thing when you're optimizing transactional memory, maybe more so than typical concurrent code. And the last is that transactional memory is probably not the right tool for everything. If your critical region is tiny, say like an XAD, then you're not going to beat atomic operations. Yeah.
Whoops.
Use your
Hey guys, so our project is Parallel Cuckoo Hash. It's a concurrent cuckoo hash map. Some background, one of the papers that we referenced made improvements upon Memcached, which is an in-memory key value store used commonly as a caching layer for API requests or database requests. And the key observation for this is that the workload of Memcached is really read heavy. There are some real-life workloads where the read to write ratio is about 30:1. And we also consider space efficiency. So with certain open address hashing implementations, such as basic linear probing, as you increase the space efficiency or the density of your hash map, the performance degrades significantly. For unsuccessful searches, it actually degrades exponentially. So for our project, we wanted to make a concurrent hash map that was optimized for read-heavy workloads while maintaining high space efficiency. And we also tried to optimize the write throughput a little bit. So we started with a basic cuckoo hashing implementation. So the idea behind cuckoo hashing is that you apply 2 hash functions to a key so that it maps the key to 2 buckets. For insertion operations, you look through all of the slots in your 2 buckets, and if there's an empty slot, you insert the key. If there are no empty slots, you randomly choose a key to evict, and you try to reinsert it elsewhere. And for read operations, you also map the key to 2 buckets, and you only have to search through those 2 buckets to look for the key. So this is good because you're guaranteed that read operations are constant time.
So these are the key optimizations that we did. The first one is log striping. Essentially, we completely eliminated logs for reads. So like logs are only now used for writes. So this means like in such a read-heavy workload, we can allow like multiple concurrent reads without like significant overhead introduced by logging. The second optimization is the idea of tag-based lookups. It's basically like a mini 2-level hash. In our original implementation, we had a struct of pointers, where like this means like for every slot that we look at, we have to do one pointer dereference, and then we have to check the keys. So this is a lot of overhead because like dereferencing is expensive, and at the same time, it's not cache mapping. So instead, what we do is like now we store a struct of tags and pointers. So instead of dereferencing the pointer and checking to see if the key matches, we do a small tag comparison. So 2 key results, like it gives us very good cache locality, because like the entire bucket can now fit on a cache line before we dereference this stuff. As you can see on these stats on the right, without the tagging, we get like around 70, 80 cache misses in the L3, and with tagging, we get 55 to 60 misses in the L3 cache. And then the second idea is like it significantly reduces the number of pointer dereferences. For the third optimization, so in our original implementation, we do path search and path eviction at the same time, where we have to kick out keys. So the problem is that it introduces a lot of false misses. So the idea is like consider a writer thread has to kick out an element. Now you kick out an element, and that element is like floating in the air. So now consider a reader thread coming in, and then trying to read that element. It would say like key not found error, and that's considered to be a false miss. So our goal is to like eliminate that as much as possible. So we found out like the path search and path eviction time, the ratio is around 2, since hash computation is pretty expensive. So what we do now is like we do path search first, and then we do evictions. So this means like we find the entire path, and then we make like evictions really quickly. So this means like we will eliminate a lot of false misses for reader threads. Now for the fourth optimization, in our original implementation, we actually had a pretty coarse lock. We lock and then we do path search and path eviction. So this means like multiple writer threads cannot like search over the path at the same time. So instead, now we do a fine-grained lock where like multiple writer threads can do concurrent path searches. But one tricky thing that we have to like take care of is the fact that like after finding a path, we have to make sure the paths don't intersect. So this is where like the validate path part comes in. So as a result, based on like our timing test, we managed to reduce the critical section by 70%.
So we measured the throughput of our various implementations, and we found that using 24 threads for the parallel implementations on late days with 90% space efficiency, our fastest implementation was roughly 12 times faster than a single-threaded unordered map. And sometimes we got 15 to 17x speed up depending on the results from our run. So this is a graph of how throughput varies as a function of space efficiency. So the interesting result here is that if you look at the tag optimization, which is the blue line on top, even as we make the hash map denser, the performance doesn't change that much. Whereas for the green line, which is the parallel cuckoo hashing without the tag optimization, as you make the table denser, the performance degrades a lot. And I think this is because without the tag optimization, you don't get as much spatial locality and you make additional pointer dereferences. And finally, we also looked at the benefit that we achieved from the lock later optimization. So in this graph, we did interleaved read and write requests. And so notice that on the top right, when we do only read requests, the lock later optimization doesn't give us any improvement because it only optimizes write requests. However, for everything else, when we do have a non-zero amount of write requests, the lock later optimization, which is the blue line, is a little bit faster than our other parallel implementations. Yeah, thank you for listening.
So was Memcached just a motivation, or did you try to play with it?
It was a motivation.
Can you say a little more how you get away with the locking?
Okay, yeah. So the idea is we maintain an array of key value counters. When an instruction thread makes modification to P, it increments the counter once before it does the modification, and then we use an atomic sync function add. And then once it's done updating it, it implements it again. So one instruction should implement the counter twice. And the idea is when you read, you take a snapshot of the counter. So if you take a snapshot of the counter before and after you're done reading the key, and if the counters change, then you know that during that read time, some other thread was modifying the key, so you have to retry.
All right, I'm Nat Jeffries, this is Madhav Iyengar, and we are Zizbit, making the world a better place with adaptive, scalable synchronization. Spin locks are a fundamental construct in computer science, and they're ideal for low latency and small critical sections because they have extremely lightweight and they have low overhead. And they're also useful in high performance computing, as we probably all found, because they don't require any OS overhead. There's no context switching, et cetera, et cetera. Unfortunately, the test and set spin lock, which is the simplest kind, doesn't scale very well. And there are a couple ways we can improve this. First of all, we can do the test and set, which requires reading in a tight loop before you try to set the global memory variable. And also, we can do an exponential backoff, which improves because it reduces the amount of contention and causes the lock to wait longer and longer as it doesn't get it again and again. Unfortunately, test and set spin locks aren't very fair, and exponential backoff only makes this problem worse.
So a lot of work has been done on different types of spin locks in the past. One of the key papers was published in 1991, which presented two new variants of spin locks, the ticket lock and a queue-based lock. And the ticket lock it's simple, you use a ticket and turn counter, and basically this ensures FIFO ordering and thus deals with the fairness aspect. But you still spin on a shared memory location, and so it's still not very scalable. The queue-based lock deals with this by making each thread, after doing an atomic access to a shared memory location, it just spins on a local stack variable, and then the next thread releases it. So it actually scales much better. Unfortunately, under low contention, the unlock path for the queue-based lock has an additional atomic operation. And because of this, the ticket lock does actually pass it up under low contention. So what we did develop was an adaptive lock which combines the performance of the ticket lock under low contention with the scalability of the queue-based lock. And the challenges of this are minimizing additional latency and maintaining fairness. So the implementation is pretty involved. So these are a few high-level aspects. So we're going to be adding the ticket lock state to the MCS lock because what we want is the better performance under low contention. We already have the scaling with the MCS lock. And so when you lock, based on the current level of contention, which we have based on the ticket in turn, you choose either the ticket path or the queue locking path. And on the unlocking side, the turn is always incremented first, so it frees anybody who's waiting on the ticket path before actually doing the atomic operation. Thus removes that from the critical path.
Our testing framework was the Xeon Phi, the late-days cluster. And our basic setup was to have a delay inside of a critical section and then a delay outside of the critical section and go through in a tight loop over those across many threads. We had a constant number of locks and unlocks for each thread. And then we had a more realistic test, which was varying the time inside and outside of the critical section as the test ran, which exercised the lock a little bit better.
So you see some basic performance, the runtimes for our basic test here. And so just looking at the runtimes, the ticket lock clearly doesn't scale very well. The MCS queue lock and our hybrid lock do perform very well. And just for comparison, we tossed in OpenMP Critical, and it's not quite so good. Now, if we normalize the runtime to the thread count, you see very clearly the hybrid lock and the MCS queue lock both scale very well as you increase the thread count. You'll also notice down there that the test and set lock actually does very well, but this is an artifact of this very simple test that doesn't care about progress of all threads, and the fact that the test and set lock is very unfair.
So like Madhav just said, fairness is extremely important, and we evaluated fairness based on, we had a bunch of threads running, and it was the number of operations, the locks and unlock pairs that happened before the last locker got the lock for the first time, which seemed to indicate pretty well how fair a lock was. You can see the test and set lock is quite unfair, as you'd expect. Critical, actually, we were surprised. The OMP critical was also quite unfair. And then ticket, MCS, and hybrid locks were all equally as fair in terms of their FIFO ordering. However, we think that the total amount of time on the critical path from locking and unlocking changes that slightly, as you can see on the graph. And then as we went to our variable workload, you can see this is over 3, 4, 5, and 6 cores. And this is a load where most of the time is spent outside the critical section, but we vary it so that there's more and less contention at various times. You can see that our hybrid lock's actually doing very well here, and it's beating out all the other locks, especially on the 4-core case. Unfortunately, if we scale out a little bit and broaden our scope, you can see that in most cases, our hybrid lock doesn't perform as well as the straight-up MCS queue lock.
So really, overall, if you have high contention or you're scaling to many cores, it really makes sense to use the MCS queue lock or another variant of a scalable lock. Under low contention, the ticket lock, if you want fairness, the ticket lock does provide pretty good performance. Fairness really doesn't matter. The test and set lock gives you the best throughput. And otherwise, you might want to use our hybrid lock.
Hi everyone, I'm Siddharth. Thank you. So our project is on accelerating Gaussian process regression on GPUs. So basically, we are trying to come up with a fast and efficient implementation of Gaussian process regression on a single node GPU. We are dealing with the constraint that both the data set as well as the data structures involved must fit in the memory of the device. And we also wish to scale it further. So let's look at some of the terms involved. So at a high level, Gaussian processes are basically like probability distributions, but unlike them, when we sample, we get a function rather than a multidimensional vector, a random variable. And GPs are basically specified by a mean function and a covariance kernel. In this project, we employ a zero mean function and a squared exponential kernel, which is fairly popular. So let's look at GP regression. So it is basically performing regression using GPs. So there is an objective function, and we basically have two different phases. One is the learning or the training phase, where we optimize the marginal likelihood by using some conjugate gradient solver, and we then obtain some parameters which we use for the testing phase or the inference phase. The total time complexity involved in this entire process is order n cube, where n is the number of data points. So let's look at our setup. We are basically dealing with NVIDIA K40 GPUs, and we have a synthetic data set, which is a sine data set, which the underlying function, the unknown function, is the sine function, which works on a 10-dimensional input data. So as a first version, we implemented a basic version in CUDA, and we implemented our own Cholesky decomposition algorithm and a recursive forward and backward substitution algorithm. We wrote efficient kernels which fuse together different operations so as to have a good performance. It is important to note that we have this implementation as our baseline rather than a single thread or a single CPU implementation. So this is a pretty strong baseline. Improvising on the baseline, we come up with the final cuGP implementation, and we employ several routines from cuBLAS and cuSolver, and we additionally use thrust routines such as parallel reduce and vector dot product for efficiency. So let's look at the performance of cuGP. So if we look at the individual components which are involved in our various stages, we can basically divide them into these 4 or 5 categories. And as you can see, we have significant speedups available for each of the different components. Specifically, if we focus on the training aspect, the learning part, regardless of whatever is the input data size, we get good speedups of around 4x as compared to our strong baseline in CUDA. And if you look at the testing phase, for higher values of input, we get a higher speed up. But however, for lower values of input, our baseline performs better because we had fused together operations in the kernel, and it performs better. But as we scale up, the cuGP performs better. So now Abhishek will continue.
Yeah, so now the question is, can we scale to higher dataset sizes? Well, unfortunately, the answer is no if we want to stick to the exact GP inference model. But the answer changes to yes if we agree to employ an approximate method, which is known as the product of GP experts algorithm. This algorithm says that we divide our input dataset into m equal sized chunks, and we employ one local GP expert to operate on each chunk. The objective function to be optimized then changes to this, which is taking a sum over the log likelihood of all local experts. Now the time complexity for this computation of each shard is now O of nk cube, where nk is the size of each shard and not the total input size, which is capital N. We call this implementation as DAKU-GP. We implement this by harnessing the power of multiple GPUs running in parallel. The number of experts is kept as the same as the number of GPUs. The input dataset is split into equal sized shards such that each shard is mapped to one GPU on a GPU expert. The communication required for this algorithm is done using low-level socket programming. And the assumption is now a bit relaxed in the sense that we say that the total dataset should be able to fit in the total combined memory that we have in all GPUs. Let's see what's going on here. We have 4 nodes here. One is a master. We have 3 slaves, each with its own GPU and one input data chunk. Now, let's say the master requests computation of the log likelihood from all of them. They get this information, start computing their local log likelihood on their GPUs. As time passes, they send the results back to the master, which uses these results, performs its update on the hyperparameters, and then sends back all the updated results to the slaves. And this keeps on going as far as the solver wants. Now let's look at the scalability. As we increase the number of GPUs from 1 to 10, the y-axis plots the time. So the total dataset is fixed at 10,000. And as we increase the number of GPUs, we also increase the number of chunks that we create. And as you can see, as we increase the number of GPUs, we get massive speedups. This is mainly because the size of the actual problem set on each GPU is small, and also because of the reduced algorithmic complexity of the algorithm itself.
So now the question arises, what if the dataset size exceeds the memory at hand? Because this is clearly a violation of the DAKU-GP assumption. So the natural question arises, can we scale better? Can we scale to higher datasets? Well, the answer is yes, by iteratively processing multiple shards on each GPUs. So the idea is similar. Basically, the input dataset is divided into multiple shards, and instead of one shard per GPU, we have multiple shards which are computed by a single GPU. So the main point, one of the one of the important points here is that both locality and data reuse are lost at the expense of scaling to arbitrary sized data sets. So let's look at an example. So here, varying from the setup that Abhishek had mentioned, we have 2 shards per each GPU, and let's say there is a request for the log likelihood computation. Each of the nodes iteratively compute the log likelihood for the 2 shards iteratively, and then send back the results back to the master. The master updates the hyperparameters, and so on. So now Abhishek will continue.
Yeah. So one small caveat with this approach is that we are again and again loading the same data from disk to DRAM and copying it back to GPU on every iteration of the solver. So we improve this performance by adding a prefetcher. What this does is it's a thread that runs in the background and fetches the next chunk from disk to DRAM even while the previous chunk is being operated upon on the GPU. And we ran some benchmarks on this and realized that this is the graph without prefetching, this is the graph with prefetching, and we see that the time reduces significantly if we add a prefetcher. Now, does this DASCO GP implementation scale to a real-world data set? So we threw a large US flight data set onto DASCO GP, which is used to predict flight delay times using 7 attributes. We subsampled the original 1 million samples from the original data set and used 4 GPUs for all our experiments. We partitioned 1 million samples into 200 shards, each with 5,000 samples. Now, this is the we slowly keep on increasing the fraction of data set that we use to perform training on. And this is 4 chunks going up to the maximum of 200 chunks. This is the time. So as you can see, the time taken as the number of chunks increases does increase, which is expected. But the point we want to make here is that the case where we had 1 million samples finished within 3 hours, which is pretty significant. So the bottom line is we have cuGP, an exact fast single node GP solver. We extend it to a distributed version called DACO GP, and finally make it extremely scalable to handle large data sets called DASCO GP. Thank you.
Okay, thank you.
I didn't quite understand why you got the superlinear scaling in your first your second performance spot in the versions. The algorithm was more efficient somehow. You're showing the training time. I assume this is time to train for the same value loss function.
Yeah, so let me look at that plot once again. The exact GPU on this one?
Yeah, that's one. So your X7X going to 41X.
Yeah.
What's going on there?
Yeah. So the important point to notice is that, as Abhishek had mentioned, if you look at the, so there are 2 things which are happening here. One is the time complexity for the algorithm itself is dependent on the shard size. So asymptotically we get a better result, and distributing across multiple GPUs this is for, we get a better speed up. So there are 2 things happening simultaneously. If you look at the computation of the complexity for computing all the shards serially, then it's m times order n cube if you have m chunks. But now imagine that we have distributed this m into m GPUs. So that m is lost, so we just have order nk cube complexity. So in that sense, we are reducing that m term, and at the same time, the shard size gets decreased because the total data set is the same, and the shard size decreases as we increase the number of GPUs. So hence, it's a cumulative effect of both the asymptotic complexity as well as the distributed.
So presumably because you're approximating more, there's a decline in quality of the result.
Yeah, exactly. Yeah. So actually, honestly speaking. So our main goal was only up to the single GPU implementation, and both this approximate as well as scaling part was not even a scaling stretch goal. So yeah, we did actually look at the testing part for both of the scaling as well as the distributed part, but we looked at the parameters that we learned, and we ported it to the serial implementation and saw that the results, as you pointed out, they will be marginally affected. But still, the ballpark remains the same as in the earlier.
So let's take a 5-minute break. We've already lost the 10 minutes that I padded in for the break. But we'll take a 5-minute break, and then we get started right at 10:05.
CG. And this is the problem we are solving. Here, A is a matrix and B is a vector, and we are going to calculate X. And here, the problem will become difficult when the A is a large and sparse matrix, and our project is used CUDA and implemented a GPU-accelerated linear solver that takes sparse matrix in CSR format.
And here we are using conjugate gradient method algorithm in our project because it is an iterative method and it is very common to use this algorithm when the matrix is very large. And here we can see that the sparse matrix and vector multiplication takes about 40% of the total running time in this algorithm. And so firstly, we are going to talk about how we implement this sparse matrix vector multiplication. Okay, and it is very obvious that each row of the matrix is independent when doing this multiplication. So our first version, SPMV, is very easy. We use one CUDA thread to process one row in the matrix. However, this implementation has many problems. The first one is that there is a huge thread divergence at the CUDA WAP level. For example, at the image, one of the thread in the WAP has much larger elements to process than the other thread. And then the other thread in the WAP have to wait until that thread finishes its job, and this is a huge thread divergence. And there are some other problems like the non-coalesced memory access and load imbalance among WAPs. In order to solve these kinds of problems, we updated our SPM to version 2, and now it can dynamically distribute a matrix row to a group of threads. Here we are using a group of threads, that is several threads to process one row in the matrix. For example, in this example, we are using four threads to process one row, and after this group finishes its job, it will try to retrieve a new row from the global row management, which actually working like a working queue in our project. And in this project, there are some rows with different lengths. And at the very beginning, WAP 0 with WAP 1, WAP 2, and WAP 3 works with row 0, row 1, row 2, and row 3. And when WAP 0 finishes its job, it retrieves row 4. And when it finishes row 4, the other WAP didn't finish their job, so it will retrieve row 5. And we can see that in this way, rows are much more evenly distributed among WAPs. And it helps alleviate load imbalance. And also, we are using several threads now to process one row, so we can now coalesce access to matrix A. But it also has some problems, like the retrieving a new row operation is an atomic operation. And if the group size is very small, for example, if the group size is 2, and now there are 16 groups in the WAP. Since the WAP size is 32, and there are 16 atomic operations in this WAP will be issued in this WAP, and it will take a lot of time to run all these atomic operations. So in order to reduce these kind of operations, we are now dynamically distribute several matrix rows to a WAP. That is, now we are using when the WAP finishes job, we send a request to GRM, and the GRM will return several rows to the WAP, and the WAP will assign one row to each group. For example, in this example, if the group size is 8 and there are 4 groups in the WAP, and the GRM will return 4 rows to the WAP. And this is the performance of our SPMV of the 3 versions, and we can see that when the variance of row length is very large, for example, the MSC matrix, which has a very large variance, and here we can see that our third version works much better than the first version, because the first version suffers from imbalance load, and also we can see that our third version works much better than the second version when the average row length is small, because the second version suffers from a contention problem. Okay.
Okay, everyone. Now let's look at how we did our inner product optimization. We are familiar with this kind of calculation. to calculate an inner product of two vectors, we have to deal with two types of computations. The first step is easy, just to assign one thread per pair of elements multiplications, and the job is done. And the hard part is the step 2. We have to implement an efficient fast parallel reduction for a very large vector. And when the vector size grows too large, the problem becomes harder because you have to deal with more complex data access patterns and localities. Before we step into our implementations, we have to introduce this shuffle operation first. This operation allows each thread to read a register value directly from another thread within the same warp. In this example, we can see by each thread executing the same piece of code, and the effect is equivalent of pushing forward all the thread values in this direction. And this kind of single instruction has several advantages. As we can see, it has low latency, and more importantly, since the warp itself has the SIMD execution style, so we do not have to introduce extra signals overhead. So it's natural to develop such an algorithm to deal with the warp level reduction. But the problem is, what can we do when the reduction is across different warps because the vector is much larger than the warp size? So here is our solution. And since we cannot communicate with threads in different warps regarding to their register level, so we have to go out of this scope. We have to communicate with different threads, but in the same block level. So what we do here is to divide this reduction procedure into two steps. The first step is to do this one round warp level reduction and store the partial results into the shared memory of this block. And then we step into the second step, and we do the reduction based on what we have in the shared memory. And this is another warp. So this is like kind of like divide and conquer and totally parallel. So there is essentially just two rounds of warp level reduction.
Okay, so we're at 8 minutes, so you have 20 seconds to present one result slide if you want to. Otherwise, you have to stop.
Okay. So this is the same idea, and we go out to the global memory. So here is our performance results. We can see that we compare our implementation with two popular libraries in this field. And this slide shows us the scalability with the metric size. And as we can see, the metric size grew from hundreds to millions, and our algorithm has a good scalability with metric size, and how the same level of the performance of the baseline, which is cool. Okay. One more sentence. Okay, one more sentence. Okay. This slide shows that our algorithm has a good stability with different metric statistics, whether it stands or it is, it deals with the workload balance. Yeah. Sorry.
So if you want to render a picture of a 3D scene, we can trace a ray from a pixel into the scene and measure how much light is on the ray path. And so for a very rough sketch, we can describe in this pseudocode. For each pixel P, we trace the camera ray of the pixel. And because each pixel is independent of each other, this loop is fully parallelizable. But there is a problem. So we can, if we take a close look at the trace ray function, we can see that most part of the algorithm is have no divergence. But for traversing the ray through the bounding volume hierarchy, there is many
divergence because different ray will traverse to different parts of the scene and to different parts of the node of the bounding volume hierarchy. So let's talk about our optimization. So the first thing we do is that we use persistent thread for better work distribution. The main idea is to maintain a global queue, and we launch enough thread to occupy the chip, and each thread will continue fetching from the global queue. And we also maintain a local worker pool to reduce the contention for the global queue. And so let's take a closer look at the traverse ray function. So if the ray finds that the node is a leaf, then it will do all the triangle ray intersection test. And if it's not a leaf, then it will intersect with each child's bounding box. And if there is an intersection, it will traverse to that child. But there is a problem because if only a thread in a warp intersect with the left child, then all other threads in the warp will wait for that thread to traverse all the subtree of the left child. So there will be much divergence. So the solution is to maintain a stack. So we can see that if only one child or only one thread intersect with the left child's bounding box, it will push the left child onto the stack. So for other threads that do not intersect with the left child, they will only be idle for a single instruction. So this will solve the divergence problem for that part. But there is a still divergence problem for the highlighted code because some thread may reach a leaf while some thread is still traversing the bounding volume hierarchy. So they will wait for the thread that reaches a leaf to finish all the ray triangle intersection tests. So what we do about this is that we use a while structure to make sure that all threads in a warp traverse and begin their triangle intersection until when they all reach a leaf. And we also employ a speculative method, that is when finding a leaf, we store the leaf in a buffer and keep on traversing until all lanes find a leaf. This will means that we can achieve full SIMD utilization in the first while loop. And ray triangle intersection test is very computation intensive, so we use this unit triangle intersection test that will reduce computation in the ray triangle intersection test because it transforms the ray into a unit triangle space. It do require some pre-computation of the transformation, but the cost is well amortized because this triangle will be tested against thousands of rays. And now comes our GPU ray tracing result. So we can see that for primary rays, even for scenes with thousands of hundreds and thousands of triangles, it can achieve millions rays per second throughput. For ambient occlusion and secondary rays, the throughput drops off because the divergence is much higher.
OK,
Okay, next I will talk about the parallel tree construction. The traditional way to build a tree is a top-down method, and it is inherently inefficient for parallelization. First, there is a sequential dependency between levels of nodes. Construction of a node cannot start until its parent is constructed. And even there is parallelism among nodes in the same level. Due to the limited width for most levels of the tree, the average utilization is very, very low and leads to poor performance speed up. So to gain more parallelism in the tree construction, we need a way to compute the children of the node directly without knowing its parent. Therefore, we use a z-order curve to arrange triangles in space linearly. The z-order curve has two properties. It fills up space, and near objects in the traversal order are near in the space. By interleaving the binary representation of the positions, we can gain a code that is consistent with z-order traversal. Based on that, we sort triangles with their code, and then we build a tree such that the tree splits where the first difference of bit representation of their code occurs. In this way, an internal node is either at the beginning or at the end of the range it belongs to, and you can see it from the figure. And now we know one end, and we can use binary search to search for the other end. This property holds for all the internal nodes. In this way, we can build the tree in fully parallel. And compared to a traditional way of construction of the tree on a single-threaded CPU, our parallel construction can achieve 200x speed up when there are 100,000 triangles. And retracing is very computation bound, so we decided to distribute the work among clusters to achieve even further speed up. And you can see from the figure, when I deliberately cite sample rate of two nodes different, the work node with lower sample rate finished most of the work because it completes one tile faster. And however, as the number of nodes increases, the speed up is not linear. And one big reason is that the tile size is not a factor of the image, and the number of tiles may not be a multiple of number of nodes. Finally, combining with our GPU retracing and distributed retracing, we can render a scene with 100,000 triangles in almost linear time. That is 0.4 seconds per image. And it takes 20 seconds to render only one image on an Intel i7 CPU with 8 threads. Thanks.
Hi everyone, my name is Yiming Wu, and this is my teammate Han Bingming. Today I'm going to show you our project. So in our project, we care about only one single thing: how to train LSTM fast on GPUs. So in case some of you don't know, LSTM is the abbreviation for non-short-term memory network. It features by getting the output of itself to the input. For example, here the blue circle is the input, the green cell is the LSTM cell, and the purple one are the output. If the LSTM model gets 3 words into the parallel programming nest, then what it will do is firstly enroll itself for 3 times, then get the output of previous layer to the next one. In this way, it can learn the whole information of the sentences, which will probably result in the prediction of the word fun or painful if our LSTM is very clever. So as you can see, it works very well in NLP and a lot of areas in machine learning. So the training procedure of LSTM is that first it have to load a batch of data, which is usually sentences. Then, as we have seen, it have to enroll itself. Then it will have to do the forward and backward. Notice that the shared parameters within the layer and the computation dependency make the parallelism of LSTM training very challenging. So one problem with LSTM training is padding. For example, here, if we want to train 4 sentences. So ideally, what we will do is to enroll a 4 length of LSTM, then 8, then 3, then 7. So the total work will be 22. However, enrolling an LSTM for each sentence is brings a lot of overhead. So what we will do is we will reuse the LSTM in a batch and pay the short sentences to the longest one. For example, here, if we pay the sentence, it will result in 30 words of training, which will be 36% of more work, which is super necessary. So bucketing is here to help. The idea of bucketing is pretty simple.
It's like make the sentences of similar length into one bucket, which will result in the same batches. For example, here, if we can reorder the training like this way, we only have to compute for 24 words, which is probably near to the ideal situation. So buckets can be auto-generated from the distribution of the word length. In our project, we use a greedy algorithm to generate the buckets that can ensure that the sentence within a bucket have the similar length. Let's look at some results. We trained a 8-layer LSTM on Pentry Bank dataset based on the code of NMAX-Net. We can see that here is the without bucketing version on one GPU. This is the auto-generated bucketing version on GPU. It achieves around 3.3 times of speed up, which is pretty good. So our first conclusion is that bucketing is super good for training LSTM.
So it's common to have more than one GPUs installed on a single machine, but there's little work to be done. There's little work done yet to explore how we can use that to train LSTM layers with multiple GPUs. So if we look at the training algorithm, we notice 2 for loops, and these are the 2 approaches we tried to solve this problem. So let me first start with data parallel. So the main idea of data parallel is to partition data over GPUs. So each GPU has a subset of data and a full copy of the model parameters. At the end of each batch, they will try to update the model parameter with a shared centralized parameter storage. So for example, in this batch, there are 4 input sequences, and each GPU takes 2 of them. And they will do the computation based on the subset of data, calculate the gradient, and at the end of this batch, we will update parameter with centralized parameter storage. So here's the result. So the x-axis is number of GPUs. The y-axis is the speed up compared to training with one GPU. So we can see we gain some speed up with this approach, but not much. And as we diagnose, the cause of this problem is that as a number of GPU increases, the communication cost increases as well because of the copy of parameter data between the center storage, which is quite huge. So this leads to another approach we tried, which is model parallel. So the main idea of model parallel is to partition the model over the GPUs. So each GPU has exclusive access to its own layer's parameter, so we don't need any shared parameter storage at all. And each GPU will do the computation only for that layer. So in this example, we have 3-layer LSTM, and each GPU handle one of layer. So GPU 1 will do the computation with layer 1 and pass the intermediate result to layer 2. And GPU 2 will take that as input and do the computation and pass to GPU 3. While GPU 2 is doing the computation, GPU 1 can load the next batch and do the computation as well. So here we form a pipeline of computation over GPUs, and we only need to pass the small intermediate results over GPUs. So here's the result for model parallel over GPUs. So we can see better speed up in this case, and we actually achieve 2.3x speed up compared to one GPU on 4 GPUs. So this is quite good. And it's also worth noticing that we can actually combine the bucketing technique with model parallel together. So in this case, we achieve 5.3x speed up with 4 GPUs. So if we go back to the question of how we train LSTM layers with multiple GPUs on a single node, so I guess the answer we have found is that we have to use model parallel because updating the parameters is a huge pain in the ass for data parallel. So model parallel has low communication cost and fast convergence. We cannot show all the results we found here, but this is the answer we have for this project. And I'd like to open up for questions for now.
How big was the network?
8 layers of LSTM with embedded layer, hidden units of 400. Then it will connect with a encoder one, which is a fully connected, and a decoder, which is also a fully connected layer with softmax above it.
It's a huge network.
And in our working, we find that because attribute or the property of the layer is different. So the memory bound or the computation bound of each layer is different. For example, here, LSTM, as it enrolled to a lot of dependency, it is very computation bound. However, on a very decent, quite decent GPU, like we used GTX 750, even the fully connect layer would not be bound. So as we have shown in the last PowerPoint, the implementation of model parallelism requires an insight into the model and the system. So we tried different partition algorithm, and we found the best one, which is just partition the LSTM regardless of all the other things, because they're not the bottleneck.
Looks like you had a speed up that is better than linear, 5.3.
5.3.
Yeah, that's combining the bucketing technique with model parallel.
Yeah, but the comparison, the baseline is the model parallel one on one GPU without bucketing, and right now we have bucketing and also model parallelism on 4 GPUs.
Yeah.
Good morning. Today we're introducing Espresso, a minimal high-performance parallel neural network framework on iOS. My name is Chi Hao, and this is Generate. So we benefit a lot from deep neural networks, from Siri to Google Photos, but all these services are online. Is it possible that we can fit this deep neural network to our mobile devices? People's impression about deep neural network is that they are computationally intensive and it takes a lot of memory. Both of which the mobile devices are good at neither. So this is why Espresso is here to rescue. So our goal is to unleash the supercomputing power inside your pocket by using high performance parallel evaluation and low memory footprint. So how do we achieve that? In addition to the normal network evaluation, we also support the compressed network evaluation. We adopt the deep compression algorithm published this year. So the basic idea is to first prune out those weights that are not necessary, and then quantize those weights with similar values to one single value to save memory. In addition to that, we do on-the-fly decompression. That is, we decompress the weights in the last minute, right before it's used, and purge the storage right after it is used to save memory. We also use sparse matrix representation and sparse matrix operations to speed up our algorithm and save memory. We also do on-demand output. That is, we only keep the outputs if they are needed in the later stage. This is very important to a DAG network architecture. So we did experiment on the SqueezeNet. It is a 66-layer network with 26 convolutional layers. It has 1.2 million weights. And we are able to shrink the memory usage, peak memory usage, by 2.7x. That is, without any optimization, our runtime memory usage is 172 megabytes, and after all the optimizations, we are able to shrink it to 66 megabytes. You know, the iPhone 6 only has 1 gigabyte of memory, so this means a lot. Because we are introducing a lot of decompression and other operations, our performance suffers a little. So we see on the CPU, it takes 1 more second to complete 1 forward pass. But actually, this performance degrade is acceptable, as we can see in the demo. We also do the same thing on the AlexNet. It is a 23-layer network with 8 convolutional and fully connected layers. It has 61 million weights. So before any optimization, it takes over 0.5 gigabyte runtime memory. And actually, this 0.5 gigabyte is estimated because we are not even able to load the whole network into our device, so we cannot measure this. But after the optimization, we are able to shrink it to 100 megabyte peak memory usage. That is, compared to our naive memory optimization technique, it achieves 3x memory. It shrinked 3 times.
So apart from the memory optimizations, we also improve our performance using the common common optimization tricks for neural networks. So the most used and most expensive layer is convolution layer. So that's why we focus on most of our effort in optimizing the convolution layer. And the imaged column is one common technique to transform the convolution into matrix multiplications. And that enables us to leverage on the CMD features provided by the CPU, and also we implemented the GPU version in Metal. Apart from that, most of the evaluations in other layers can be structured as matrix multiplications. So that's we can apply CMD as well in these places, and we also fully utilize the spatial locality in all the other places. So by applying these optimizations, we are able to achieve over 250 times speed up over the naive implementation on CPU. And we can see that AlexNet is faster than the SqueezeNet because SqueezeNet has far more layers, and also we can see that from the AlexNet takes the weights matrix for the AlexNet is more sparse, so that's how our sparse matrix multiplication is taking effect.
So let's see a quick demo. So this demo is running on an iOS 6. It's this device, and I like to give my phone to Kivon. Do you mind being our first user? Okay. So, yeah. And you need to share your testimonial after your... Oh, sure. Okay. For people who cannot use my phone, this is a video we made like several days ago. And running on this iOS device is a SqueezeNet, which has 66 layers. And this is a CPU version, and Kivon is using a GPU version, and it's 1.5 times faster. And we see that we can get recognition in less than 7 seconds, and it's a very, very acceptable time since we are using a mobile device, and we cannot expect much because this is not cafe. But it's usable. And we think it's quite accurate, although this is not our... It's not our. It's because of the SqueezeNet. It's not our thing.
Are these ImageNet categories?
Yeah, it's the ImageNet category. Okay, so I think it's about the time. So what do you think, Kivon?
Hold on. I was able to reproduce that result.
Oh, okay.
But it thought that Kevin was a bassoon.
Yeah.
But I was able to reproduce that one when I took a picture of the. Yep, and it ran in about what you said it was.
Okay. Thank you.
Yeah, these speed ups measured in continuous state when the phone is thermally limited, or what's the startup?
Oh, or the startup.
Okay. What does it drop to when you become thermally limited?
Actually, I don't know. Because actually, this thing doesn't take much time to run, and evaluate it only takes several seconds, especially when you are running on GPU. It's very, so on the Xcode it shows the power impact is high, but high means, because it has very high and, so high means it's reasonable. So, I don't know, because you run anything, it shows high. So, we didn't do experiment on your thermal limit thing.
What resolution image are you feeding in?
Any resolution, but we will resize it to 227 by 227, so it's according to ImageNet. Okay, thank you.
In our project, it's fast trained from my library on CPU. We know that CPU, is very expensive. The training is usually done on GPU, but we will deploying our model in that or in user species and mobile phone. It's really too expensive or impossible to have GPU.
That's why we runtime lighting on CPUs. And at the beginning of the project, we tried to write in Halide, and we implement FFT and direct convolution, this algorithm, and by optimizing some memory layout and kernel sizes, we can beat Caffe in most cases except for a few. And then we tried to write binary CNN in Halide, but we found it's hard to improve the performance with our rough implementation because Halide doesn't have a support for the bit types. So it prevents us from a lot of optimization using bitwise operation. So that brings us to what we really want to talk about today, which is binary CNN implemented in C++. And so there are ambiguity in the terms, so to clarify a bit, the binary CNN we work on is a kind of network where all the weights parameters and all the intermediate inputs and outputs, they're all in either -1 or 1. And it's very recently that researchers have found out techniques to actually train those networks and still get a reasonable accuracy. And the benefit of such a network is obvious. It saves you a lot of power on mobile devices, and it saves you memory, and presumably it could run much faster. So this makes it a great candidate for industrial use. However, there are not a good implementation available out there because the major challenge is like how to really use bitwise operations to compute what you need. So let's do it. In the core of like all convolutional layers and fully connected layers, the core operation is dot product, where you multiply two sequence element-wise and compute the sum. But now if you multiply in two elements that are either -1 or 1, you only care if they are equal or not. So you can represent your data as a bit sequence and then do an exclusive OR of these two sequences. And by counting the number of zeros and ones, you know how many of them are different and how many of them are not. And you can get the dot product by subtract this number. And since we know the length of the sequence, we only need to compute the number of the ones in the sequence, which is what we know as pop count. And to compute a pop count quickly of a long sequence, we adopt a technique using a lookup table. So here, assuming the input is the 256 bits SIMD vector, we first build a lookup table containing the pop count value of every integer less than 16, which is every 4-bit integer. And we store this table in a SIMD vector. And by using some internal intrinsics, like first we bitwise AND the input with the mask to take out every other 4-bit blocks. And by using a shuffle instruction, we can basically look up the 4-bit block in the lookup table to find out the pop count of every 4-bit block. And we do this again by for the rest of the 4-bit blocks by first shift the original input by 4 bits and do the AND and shuffle again. So by adding this result together, we can get the pop count of every 8-bit blocks in this SIMD vector by using 7 instructions. And actually, if you're using the dedicated pop count instructions in Intel, it only operates on 64 bits, so you need 4 pop count and 4 add, which is 8 instructions in total for 256 bits. And in some real tests, we did find out this works a little bit faster than using the pop count instruction. And we will do this again and again. While we're scanning through the long sequence, we get a pop count, and we can add them at last to get the final value. And you can see that this implementation is highly arithmetic intensive. And for convolutional layer, we can use this kernel directly by first slicing the input from the input images and take the kernel. And originally, we will need to compute the dot product of these two. But now we can use the pop count kernel and inclusive OR. And there are other optimizations we can do here. For example, we actually don't need the pop count, we actually don't need the dot product, the value of the dot product, because we will have to quantize the value back to -1 or 1. So we will need to know the sign of that value. So there are other optimization for a specific type of layer we can use. And so we verify that this implementation is highly arithmetic intensive. Like this is the result from Intel VTune amplifier, and they show that the program is highly core bound, which means compute bound, rather than memory bound, and it shows a very good clocks per instruction rate, which is 0.56. And the speed compares to Caffe. So here's the computation time, how the computation time changes with different image sizes and kernel sizes. And we can see this is single thread cases, and we can see that the speed is usually 10 to 12 faster than the floating point version in Caffe. And our implementation scales better than Caffe. In multi-threading cases, it can sometimes run up to 20x faster than the floating point version. And yeah, so that's about it. That's it. Thank you.
Did you look at the classification accuracy, or did that match with the slide we showed at the beginning?
Those papers are very recent, and I tried to reproduce them. I cannot get the very similar accuracy, but it's much better.
Yes, sir.
Our topic is to implement neural networks on FPGA. And as we all know that these neural networks can have reached the state of art in speech and in image recognition. And running a neural network on standalone devices can quickly drain the battery, but we want to provide an always-on service. And FPGA is energy efficient, but only toy networks until recently. And those implementations are suffered from high latency and low scalability. Our goal is to implement a neural network on FPGA to recognize digits. And because neural networks usually have high computational cost, so we want to achieve high parallelism. And also wanted to scale with the size and depth of neural networks. A fully connected neural networks with n nodes usually have n square weights, and which means in our scenario, which means 4 million weights, and which is equivalent to 4 million interconnections. But FPGA only have limited amount of logic cells and interconnections.
So the normal workload pattern of matrix multiplication is not suitable for FPGA, so we need to reschedule the work. The intuition is that instead of a direct connect from node 1 to node 2, we can use an indirect connect from node 1 to node 2, so we can reduce the interconnections from n squared to 2n. And so let's see an example. We first paint the matrix, and we do a simple multiplication, and the results is shown in the bottom. And we can rearrange the results due to the commutative property of the addition. And we can see that the first column is 1, 2, 3, which is our initial input, and the second column is the one shift from the first column, and the third column is the one shift from the second column. And then we can use our intuition that we just use a shift combined with a multiplication to get our final result. And first we multiply with blue weights and get a partial sum and shift it, and multiply with the yellow weights and get a result, and then shift and multiply with red weights. So essentially, we can read from the diagonal from the matrix, and for each run we shift the inputs, and the result is the same. By doing this, we can reduce the interconnections from 4 million to 8,000 in our scenario, and the number of interconnections now goes O(n) instead of O(n) squared with the number of nodes, which is much more scalable.
Okay, but there still exists a problem is that different layers can have different different numbers of nodes. So our network have different number of nodes on the first and last layer of networks. So we would like to reuse the same module or hardware module for different layers. So we try to pack the first layer and last layer with zeros. And in this case, all layers share the same module, and resource usage stays constant with the growing number of layers. To further save resources, we try to implement bitwise neural network. And all weights are only 0 and 1. And more important is that we can replace floating point multiplication with XNOR. And also we can use inactive weights to improve accuracy, so that we can use matrix padding for free, because we can set the padding weights with inactive weights. And the result seems good because accuracy only drops by 0.2%.
Now we have combining our previous ideas. Now we can have our final hardware module, which combines with Swift and XNOR and enable signal and a counter. Then finally we go through a activation layer, which is essentially a comparator, and we got a output, and the output is input into the next layer, and we next layer still use the same module and re-input from the layer 1. And when we implement our algorithm, we found that our program is bandwidth bound. So simple idea is to use batch processing to amortize the cost of loading. The idea is very simple, just copy and paste the same module several times until we reach the resource limit. Now every module goes through the same procedure, so we can share the same weight load from the memory. We run our test on the Altero educational board. The result is that the serial version needs over 6 million cycles for compute and 1 million cycles for a load. Our parallel algorithm can achieve a 10-24-week parallelism, so the compute cycles are almost always gone. And when we use the batch process, we can batch process 3 images given the hardware resources we have. Now we can further amortize the loading cost by 3 times. We also compare our design with the TensorFlow design on the CPU. The CPU is 50 times faster than our FPGA core, but the throughput is very similar. Also, our code achieves 800 times better energy efficiency. Also, we compare our algorithm with a recent paper. We achieve 4 times more throughput than a recent paper, and we have much better latency than a recent paper because the paper used a batch size of 100 to exchange the latency for throughput. So the latency is very high. We achieve 60 times more throughput than a recent paper. Also, we have 2 times better energy efficiency. Thank you.
Yes. Okay. Hey everyone, we are Athilis. I'm Ishan. This is Karan. So we are basically an artificial graph generation library. So I'll just dive right into it. What are we doing? We are generating artificial graphs. We'll be using OpenMP, pthreads, and CUDA as an evaluation tool. And the idea is very simple. The idea is to compare implementation complexity, speed, and resource efficiency across the 3 libraries. Now, why do we need large-scale graphs? Well, all of us did work on the 3rd assignment, and suppose, let's say, take the Twitter graph. Suppose you want the same graph properties, but you want, say, the 10x amount of edges or 10x amount of vertices. Such a library will help in that case. You can scale your data analysis tools and check if your tools are scaling. Unfortunately, the sequential algorithms are very slow, so we thought there has to be a parallel way of doing this, and there is. So let me just define what we are trying to do. So the input that we receive from the user is a probability distribution over which to generate the graph, the number of edges that the graph should have, and the number of vertices, and some graph properties which can be directed graphs, sorted graphs, cyclic graphs, or whatever. And outputs traditionally, the libraries that we have right now output a tab-separated list of edges, which is a concern for us because a tab-separated list of edges is, while storing, it will cause problems because each edge is at least 2 ins or 2 longs. So that's not efficient at all. And the output is a graph in memory. It doesn't necessarily have to be a graph written out to a file. Now, the traditional parallelism that exists in graphs is over nodes and vertices. And the baseline that we'll be using is an implementation library from Berkeley called PowerMat. And for analysis, we'll be using Snap from Stanford. Now, the paper that we are following is actually from CMU. It's called Recursive Matrices. The idea is very simple. Given a matrix, a 2x2 matrix of probabilities, you recursively traverse the graph and you build the graph. So I'll just give an example. Suppose we want to generate a 4x4 graph and we have this probability distribution. We'll just select a random number, compare where it lies in the cumulative probability distribution. In this case, suppose the random number is 0.3, it lies in the first quadrant. Now you go into that quadrant and divide it further and generate another random number. In this case, it's 0.99, so it is this quadrant corresponding to this quadrant. So effectively, we have an edge that has been generated, which is 1, 1. And we'll represent this as A and D because we went into the A quadrant and then into the D quadrant. And this is important. We'll just come back to this later. So this is effectively, we are breaking the graph up into small squares. So the parallelism that we are doing is not over nodes or vertices, but it's over these squares. Now, we can do this parallelism using OpenMP, pthreads, or CUDA. I already gave away the answer, but we are doing all three. So the algorithm is rather simple. So as a high-level implementation, because we want to jump to the analysis and the results as soon as possible, is that in pthreads, we are using two-level queuing. So one level of queuing is a worker node, a worker queue to generate the edges over squares, and the other is a producer-consumer queue to sort of write to memory. In OpenMP, we are ensuring thread independence, and we sort of experiment with different scheduling schemes. Now in CUDA, we all know we can do two levels of parallelism. One is over the block, and then each block has a number of threads in it. So you have to exploit the block locality, which we are doing. And the shatter square means like we are sort of balancing the matrix a little differently in CUDA to ensure that the blocks get used as much as possible. Now moving on to the analysis, Karan will take over.
So our aim is actually to evaluate memory footprint and the total runtime as a function of the input variables, which are the probabilities, A, B, C, and D, the number of edges, the number of vertices, and different number of threads and number of blocks. So starting off, so how do we know that our algorithm is actually correct? So we actually compared the out degree distributions and a couple of other graph properties with a graph generated by Snap, and we actually plotted these values and saw that our graph is correct. So a problem that we encountered with the original implementation of this graph generation was load balancing. So here we actually skew the probabilities on A. So we put most of the probability mass on A, and so as we can see that the runtime actually goes it goes like 2x. So that is not good. So that means but the number of edges remain the same, and our total workload is proportional to the number of edges. So that means we have a load balancing issue. So we solve that using the shatter square that Ishan just described. Another problem that we faced was memory copy time. So when we ported this code to CUDA, as we increase the number of edges, so this is a log-log graph. So as we increase the number of edges, the memory copy time starts taking up like half of the total time of the code, which is actually not good. So so what can we do to reduce? So why is this the case? So so as we increase the number of edges, the graph representation size actually grows up. So what we try to do is try to compress the graph. So most sparse representations are ill-suited for this because they require the whole graph in memory to actually compress the graph. So until now, what we are assuming is that all edges are equally likely while actually storing the graph. So we kind of propose a Huffman encoding scheme to actually compress compress the number of bits required to store an edge. So as Ishan said earlier, edge can also be represented by the number of choices, by the choices that you make. So like it can be represented by A and D. So because A is way more, so say A is way more probable than the other probabilities. So the number of bits required to store edge in that A block should be less, right? So we kind of use that intuition, and this actually shows the compressibility factor as a ratio so we plotted the the probabilities on the x-axis, and we distributed the rest of the probability mass uniformly over B, C, and D.
Okay, 1 minute left. Okay.
So we come to the results.
Okay, I will go to the results. So this is the CPU implementation scaling across threads on late days. So you can see that the original, which was also a P-thread implementation but didn't have load balancing. So when we implemented the load balancing and the two worker queues, both P-threads and the OpenMPs scale pretty well. And so one problem with CUDA has been the tuning. So if we increase the number of graphs, the number of edges to generate, the sweet point of blocks versus threads keeps moving. Now, before showing...
Yeah, last 10 seconds. We're at 8 minutes.
Okay, fine. Disclaimer out. So this is the scaling across the number of edges. The disclaimer was there is an overhead in CUDA if this is a log-log graph. So it's not like we're not going to claim that at least for this operation, fine, CUDA is performing the best, but that's not a generality that we're going to claim on. And so memory footprint, we wanted to optimize, and that was the compression. And because the graphs are not uniformly random, so we were able to compare the three things pretty well.
Yeah, sorry. We can read it though.
Yeah.
So did you compare it to format? Hello everyone, this is Ran, and it's my time presentation. We're going to present the log rate implementation of B plus tree. So why B plus tree is hard to be implemented as a log radial structure. Suppose here we insert a key 34 into the tree, and after we insert the key, the leaf nodes may have to be split. So this split will again insert a new key into the parent's node, and parent will split again insert a new key into the parents, not all the way up to the roots. So one single modification to the leaf nodes may modify the whole tree on all layers. So here is our implementation of Pong tree. This is an Intel design of a log-free B plus tree. So the main idea is a bulk synchronizing stage design. We partition the operation of queries into multiple stages. In the first stage, we batch the queries and distribute these queries to a pool of workers. And then the workers will search down the tree to locate the leaf node that is for the query. And then the modification for the leaf nodes, after we locate the leaf nodes, we group the modification on a node by node base and group them and redistribute the tasks to the workers by nodes. So here that we guarantee that a single worker has exclusive access to the node that is going to modify. So this is to avoid risk conditions. Then we apply those modifications. We may have merge and split of the tree, and the modifications are propagated up to the root on each layer. And then on the final stage, we have one single thread that will handle the special case of root nodes, because the root nodes split and merge may decrease or increase the height of the tree. So then we go to stage 0 again and do another batch of queries. So here is an illustration. We have 5 queries on the right side. First of all, first the 5 queries are batched and then assigned to different workers. We have 5 worker threads, where each one will be responsible for 1 query. And we search down the tree to locate the leaf nodes for those queries by the key of the query. And then after at this point, the search results can be directly retrieved from the leaf nodes. So R2 and R3 can actually get the results immediately, but it will only respond to the client or the corner after the tree modifications are done. Then the tree modifications are grouped into each node. The R4 and R5, because they both modified node 4, is grouped together and assigned to a single thread, and another thread will handle node 6 modification. So we apply the modification. We delete root node key 8 and 12 and add another key 40. This deletion will cause a merge on node 4, and that insertion will cause a split. The merge and split are reported to the upper layer, and then each modification on the internal nodes are assigned to one single thread for each node. So the key 8 is deleted, and another key 40 is inserted. Then we see that node 2 has another split. So it reports to the root node again, and then we have reached the final stage that is the single root will be splitted. We add another key 40, and the new root will be allocated in this case. And it will point to the old root and the newly split out child. All right, this is the basic algorithm of Palm tree, and we have done several optimization to the implementation. The first thing is to pre-store the query. Pre-store the queries by key to balance the workload, because in the workload distribution, each worker will grab a portion of the task to handle. And then we replace malloc with jmalloc. There's many memory allocations to maintain the structure of the tree. And malloc is totally not scalable on a multi-core system. Jmalloc is actually much better than that. And for the key lookups, during the internal nodes and if nodes, we use SIMD intrinsics to look up keys using SIMD. And then the last one is really important to reduce the communication between each stages. On the previous slides, we have seen that there's a synchronization point between each stage of the operation. And to reduce the communication time, especially for task distribution, we actually cut down the communication a lot. So here is our evaluation of the implemented Palm tree. So in the bottom, the blue line is the baseline, which is totally not scalable. And we add after the optimization of pre-sort, it's still not scalable, because the system is totally bounded by memory allocator. So after we replace malloc with jmalloc, we can scale up to 6 cores with around 8 million of operations per second. And then we add SIMD, we go to 15 million of transactions per second, operations per second. And the most important one is that after we reduce communication, we can scale well to 16 cores and reaches and achieve 60 million of operations per second. And then here's the speed up comparing to single thread. With different tree size, for small trees with 500,000 of keys and medium-sized trees with 5 million of keys, we have a nearly 16 times speed up over a single thread. And for a large tree with 50 million of keys, because the memory throughput could be a problem, we suppose, so the speed up is not as good. And this workload is 80% of reads and 20% of updates. And then this implementation is also resilient to skewed access. So here, the 80% of the access goes to 20% of the keys. And for different tree sets, we can see that the throughput is actually no big difference between a uniform access and skewed access. And the next one is the comparison over, we have implemented a fine-grained locking B+ tree, which is not so performant. So it can only scale to 4 threads. And we also compare with single thread standard map and single thread B tree. We try to add a spin lock or a rewrite lock to those data structures, and actually they perform even worse when those locks are added. So this is, and then we have a final chart about the runtime decomposition of the implementation. We can see from the green bar is the most expensive operation in the tree. It's in stage 2. Stage 2 is actually scan the leaf nodes and insert or remove keys from leaf nodes. But when we'll have more cores, this is not that significant. So the synchronization time from 1 thread to 16 threads has increased. The portion of synchronization has become larger and larger, and we can expect that will be a major bottleneck when we scale to even more threads. So this is our lock-free B+ tree. Thanks.
This and that works. Okay. All right. Hi, I'm Joe Doyle.
Hi, I'm Rachel Kositsky.
And we created for our 418 project OmegaGo. It is an elastic, highly distributed Go AI tournament system. And we'll get into what all that means as we move along. So first off, the game of Go is like chess, but it is way harder for a computer to play. You have 2 players, black and white. Each of them places stones on a 19 by 19 grid, and your goal is to surround territory and surround opponent's stones in order to get points and win the game. The core difficulty for developing artificial intelligence for Go is that there are many, many more possible games. Its branching factor is much higher than chess. There are more than 200 orders of magnitude more games, more possible games in Go than in chess. All of the techniques that work great in chess for exhaustive tree search and A/B pruning don't work well for Go. So in January, Google DeepMind managed to change that a little bit. So these are a bunch of different players ranked. In red right here, we have all the previous best AIs. These are based off of Monte Carlo tree search, which we'll get into later. This is Fan Hui. Fan Hui was the European champion at the time, European Go champion at the time. This is Google DeepMind's product, AlphaGo. There are two versions of it. And you can see that it is ranked higher than Fan Hui. And at the time of publication in Nature in January, AlphaGo had already soundly won a series of matches against Fan Hui. So within AlphaGo, there are many different feature sets. There are like 3 core features that they can turn on and off. And we decided that we wanted to take one particular set of features and see how much we could implement that. So we took the policy network and the Monte Carlo rollouts and attempted to see how we could make that happen. So Monte Carlo tree search is based on, it's a probabilistic method for figuring out the best move. So every node in these trees is a board state, and each node has an expected win probability, as well as the number of the experimental significance, the number of samples. So the Monte Carlo tree search runs by picking the best move that you know in the tree until you reach a point where you don't have any data. You then create a new node and start playing random moves for each player until the end of the game. And then you compute who wins, and you propagate that result back up the tree to improve the estimate. We implemented this with C++ atomic containers, and we're able to make this totally lock-free, which means that we can run more of these simulations repeatedly, and this leads to a higher accuracy. And you don't have to care that much about race conditions because they're not statistically significant. Yeah, so that's Monte Carlo tree search and why it's parallelizable. The other part is a policy neural network. So a policy network is a deep convolutional network. AlphaGo ran with a 13-layer policy network. We made some smaller ones because we don't have as many computers. And the basic idea is that this takes in a matrix of a bunch of features of the current board state and outputs a probability distribution over the possible legal moves. So you can combine this with Monte Carlo tree search to create an asynchronous policy MCTS, where you have an extra thread doing probabilistic traversals of the tree and running the policy network when it finds something that hasn't had it run yet. This means that the policy network can provide hypotheses for the Monte Carlo tree search to test. So we trained on late days. These were on worker nodes. We were using a library called TinyCNN. It is a CPU-based OpenMP and AVX accelerated convolutional neural network library. So around May 5, we discovered a horrible catastrophic bug in how we were extracting features, and so I had to totally restart the training on these networks. But we were training these 4 networks, and we've reached about 32% on the training data set of 70,000 skilled amateur games. AlphaGo improved the state of the art on this data set from 44% to 57%, so we're doing all right.
So we've developed these different Go AIs, MCTS, APMCTS, each with different numbers of threads. And we want to compare these different AIs and see how well they played. And the way that we do that is that we have them play games against each other. So we developed a distributed system that hosts tournaments of different Go AIs. However, running the system on 2 laptop computers wouldn't have let us play very many games over the course of this project. So we took Professor Kayvon's advice to use whatever systems we could get our hands on to heart, and we recruited the available machines in the Gates clusters and the Unix clusters. So our system scales up the number of games that it plays when there are more available machines and scales down appropriately. Here we have a graph of the games played per hour over the last week. At the start of the week, we had many resources available. We had a peak throughput of 150 games per hour. Then exams happened, and many of the Gates machines were unavailable for use. So we scaled down appropriately and didn't hog all of the resources in the remaining machines. After exams were over the weekend, we again ramped up the number of games we played per hour. Overall, during the course of the past week, we played over 5,700 games. Here we have a representation of our results. So here's a bar graph of the win rate against a baseline heuristic AI by MCTS AIs with different numbers of threads. Here, with one thread, we achieved a 59% win rate against a baseline heuristic AI. As we increased the number of threads, we got up to 89 to 90% win rate. When we added in neural networks and had the asynchronous policy MCTS AI, we achieved a 100% win rate against the baseline AI. So this shows that adding more threads, parallelizing when you have a limited number of time, leads to increases in performance.
And I think we have time for a very, very short demo.
So here we will be showing the tournament server in action. It's over there.
That's the
So
one.
these are games past, present, and future that are running. At the top, we have the number of workers which are running the AIs, and the number of CPUs used and number of available CPUs across all of the workers.
Yeah, so we can actually look at one of these games in progress. If you know much about playing Go, please don't cry. These are not nearly as good as humans because, like, for example, Google's baseline neural network took 50 GPUs 3 weeks to train. We didn't have that. Yeah, we made do with the large amount of things we had. But we've had games running for quite a bit, and you can see all of the workers we currently have online and what their available resources are. For what this looks like, if you have a bunch of these SSH terminals open, it's
It's pretty great.
Oh, did I close it? Oh no, it's that one. Here we go. This is quite a lot of machines running AIs.
So,
Yeah.
are there any questions?
Yeah.
Okay, so you're not doing any training at this point. So you did all the training once, and at this point they're playing.
We still have late days jobs in the queue, actually as late days completes jobs, it copies the neural network weight files back into AFS, and since all these are on AFS, it will always run with the latest version of the neural network. However, the training is not fast enough to see big differences very quickly.
Okay, so I'd like to thank all the speakers. There's pizza outside, and I guess the judges will deliberate, and we'll eat pizza, and I believe we were promised a demo of hacking servers. So that will go on as well. Okay, thank you. I'm going to cede the floor to the judges. And so you're going to announce in backwards order. Yes, right? Okay, so they're going to announce like runners up n-1 through 0. And then so that means that you can come up here and stand so we can all acknowledge you. But you can't pick your prize until the winner's announced because they can go first. Alright,
so n equals 7, it turns out. I guess just as preliminaries, of course it's really hard to pick 7. We were aiming for 4 or 5, and 7 wasn't enough, so I want to congratulate everyone on some really, really solid work. We tried to pick a diversity of projects. I think you might notice that as we did the winners. We also somewhat emphasized projects that they're really solid projects with a lot of work in them, where the parallel computing aspect wasn't so key, and so we took that into account.
Yeah, I was going to say, I think it was really, we looked at what people really had to do, and I think, I'm really impressed, of course, some very difficult problems that you took on, and those of us that are in the industry, they're not easy, so congratulations to all of you.
Yeah, so this was a lot of fun. And the other thing to bear in mind is, we had to make these decisions in like 10 minutes, right? Unlimited information. So if you feel it was unfair, it's impossible at the pace. It's hard to know exactly what everybody did.
You didn't drive the judges enough.
We did our best, and they're all hard decisions. So here we go. So number 7 is PIMD, and the thing we particularly liked about that, it was designing a tool. Interface for parallel programming, which wasn't really something.
This is PyMD. Sorry, PyMD.
Yeah, PyMD. Go ahead and pick.
No, pick anyone.
Yes. Okay. So number 6 is Paracuckoo hash. Algorithmic work and analysis. Number 5 is the GPU ray tracing project. That was a lot of work to get that working, and there was also a data structure and instructions component to it, which is hard. So number 4 was Athelas, the graph generation system. Thorough evaluation and methodology, presenting the results, and also implemented on 3 platforms and compared them, which was interesting. So number 3 is AlphaGo. This one was a distributed system problem, right? Focused on running on a bunch of different machines, and was a complete system, which is always interesting and is hard to do.
Also, OmegaGo, we're less good than Google.
And it's also a very interesting problem space. So number 2 was the FPGA neural networks project. Hardware project, and so you can get really massive parallels in one an FPGA. And it's a lot of, anybody who's worked on hardware, it's a lot of work to get hardware to do anything. So that's great. And then finally, the winner is Espresso. So that was a very complete system with some hard parallelism parts as part of it as well. Yeah, so it's a lot of fun.
Congratulations. So I think we'll just go down the list.
We didn't expect we will get anything, so I stay here for the pizza.
Okay. Do you think you can pick something that for it. So here, you should fix it for yourself first.
Oh, so I have to do two?
Well, yeah, one per person.
Oh. So I will take.
So you want one person to each patient.
Okay, I will take two. So the long and which one is the high?
You should take it back. Okay. So we have, oh, that's an Oculus DK2. It's not a shipping Oculus.